So having been here now for 2 days, I quick scrambled and changed my talk. So I hope I've not falsely advertised. I thought we maybe would do a little math. I mean, it's Saturday morning. What better time to do a little math? So I'm going to walk you through an activity. Some of it you doing, some of it I'm going to fast forward so you can see where it's going. And then we can debrief a bit after that. I will ask as a favor that if you have seen this exact topic before, to please let other people figure it out. I'd very much appreciate that. So here is the question we're going to start with. This is the first question my students get. Is every integer the sum of factorials? And here's the first few factorials in case you forget. And that's a pretty broad question. So usually the first actual question I give them, and I'd like you to think about it for a sec, is, can you write the integer 10 as a sum of factorials? I'd like you to get something to write without, get something to write on out, or at least imagine doing so, and to write 10 as a sum of factorials. No, 0 factorials off limits, sorry, no go. Do you know what I'm asking? No, just add up some factorials. So you can work with 1, 2, 6. You ought to be able to figure out a way to add up those kind of numbers. You can repeat numbers, is that what you're asking? Yeah, absolutely.
And 1 factorial is presumably ruled out?
No, you can use 1 factorial you want. This is not supposed to be hard. This is the warm-up, okay? Everyone is supposed to get this right, okay? Hopefully. It's a group of mathematicians. You never know. Okay. Would you do me a favor? Would you tell your neighbor what you did? All right. So I'm going to ask a pair to tell me, a pair who got 2 different ways of doing it, to tell me the 2 different ways. The up front where the mic is sounds great.
Okay, so I did 3 factorial plus 2 factorial plus 2 factorial.
That works.
1 factorial plus 1 factorial plus 1 factorial, et cetera.
That works too. Thank you for that. And how many of you had something different than those 2? Those are usually the popular 2, but way to be outside the box, I appreciate it. And I think based on our second answer here, you would agree with me that it can be done for every integer. So my question's answered, yes, just 1 factorial plus 1 factorial till the cows come home. Yes,
But how about negative?
Oh, just positive integers. Thank you. So for negative, the answer here would be no. There we go. We have an answer there too. Fabulous. Okay, so any positive integers, so thank you. I needed to make that less vague, right? And this is something we do in class. Things are not always exactly specific, and we have to fine-tune it, so thank you for asking that. Now, the answer to does it exist is yes. So what I'm actually interested in is, can I do it as sort of efficiently as possible, using as few factorials as possible? In other words, is there sort of a minimal way to do it? And for 10, what you did, 3 factorial plus 2 factorial plus 2 factorial, uses the fewest factorials possible. So one of the questions, and I'll give you some more data before we play with this, is how I would know if it was minimal. And then for my students, the instructions would be to state your answer as a conjecture. So because you're a group of mathematicians, I'm going to fast forward and show you a more rigorous definition, because I think you'll find it easier to answer these questions there. But for my students, we don't necessarily need that. So here is the formal notation for what I'll call a factorial representation. The integer n is a sum of non-negative integers times various factorials for as long as you need to go, basically. And so my students will write something like this, and minimal representation will kind of come to an agreement that it means there's the fewest factorials possible means the sum of those coefficients. So I'm no longer doing 2 factorial plus 2 factorial. I'm doing twice 2 factorial to be more efficient. So now I want to ask you that question again. And I'm going to ask you to try to write something down, and then in a little bit we'll turn to a neighbor. So how could you look at the sum of a sub k, k factorial, and looking at those coefficients, a sub k, how could you tell if this was minimal? I had used as few as possible. So I'd like you to try to write something down. So what do I mean? What are you supposed to be doing? I think you should pick your neighbor's brain now. Ask them, do you know what she's doing? Do you know how to do this? What's going on? What should this be? I'm looking for what would you notice about a sub k that would tell you it's minimal? We're going to return to big group, even though I know that wasn't enough time. Is there someone who thinks they have it who'd like to share? Who's?
Well, I have conjecture.
Go for it. But here comes the mic.
Who was that?
Oh, don't fight over it.
We do not have a complete answer, but it's really clear that AK should not be K plus 1.
Great idea. Can anyone add to that? Can we improve it? Same thing, huh? Yeah. Okay, you were right. And why is it that you can't use K plus 1? Why would K plus 1 not be a good coefficient? Oh, sorry. Yeah, you can just run your tail off here today. Sorry about that.
Because then you could have a K plus 1 factorial, and that K would become a 1.
Yes, yes. So if you have, for example, 2 factorial plus 2 factorial, that's fine. But if you had 2 factorial plus 2 factorial plus 2 factorial, that's 3 copies of 2 factorial, which is 6, which is 3 factorial. So in fact, I will fast forward a little bit for you here again. In fact, as long as the a sub k's are less than or equal to k, it's minimal. The only way it turns out, the only way that you could be using too many factorials is exactly what you said. That you have k plus 1 or more of k factorial. So I didn't actually prove that, but that's OK. And then I should mention that the fact that there's a minimal one exists because this is a discrete math class and not a real analysis class. So if you can write it one way, you can just write it as shortly as possible. But the question becomes then, is it unique? And so this is the next thing that students will often either posit. I think it's not unique is usually what they say, because it sounds too complicated to be unique. Or I think it's unique, but I certainly don't have any way to prove it. So I want to fast forward a little bit and show you a key identity that's used in that proof. Not the proof itself. It's Saturday morning. OK. And the key identity is to ask a new question, which is, what is the largest integer you can build up using from 1 factorial, 2 factorial, all the way up to n factorial? And normally my students would grapple this a lot more, but again, I'm going to fast forward a little bit for you here. So I will give you some data to look at to build your conjecture. So if you can only use 1 factorial, and if you're going for minimal, so you can't put a 2 in front of it, then the biggest number you can get is 1 times 1 factorial, which is 1. And if you're allowed to also use 2 factorial, you can do 1 times 2 factorial plus 2 times 2 factorial. I can't talk today, which is 5. So this might not be enough data. So students would do more. Do you see what I'm doing here? Yeah? OK. And more. And some of you have seen this before, so shh. OK? Will you write down what you see here? What do you notice? And make a conjecture. What's going on? Will you write something down? And you can help your neighbor if you want. Wake them up. What's going on? What's she doing? You know? OK. Again, everything I'm doing here would be with much more time. So go way back this time. Go find someone in the back who, yeah. Someone wants to share in the back, so done or not, we're going to hear some answers. Sorry. Oh, give it to Judith. She's awake. Oh, no.
There.
Will someone share their conjecture with us, please?
It's a factorial minus 1.
It's a factorial minus 1. Yes, it is. Now, can someone refine that for us? If I go up to n factorial, which factorial minus 1 is it? Oh, come on, you want to say? In terms of n, do you know what? It doesn't have to be the same person. That person just...
N plus 1 factorial?
Thank you, sir. Thanks for playing along. Now, that is much easier for us as mathematicians to say n plus 1 out loud than it is for our students, right? So you can see where we're building some writing and other skills here. So we have a conjecture. Many of you may recognize this identity. Its nickname is the third proof by mathematical induction. The first proof in most textbooks is the sum of the first n integers or something like that. And the next one's a geometric. And the third one's usually this. It's a very cute short proof by induction. Matter of fact, later in the course, we will prove this 3 different ways. It's a telescoping sum, which if you realize k is k plus 1 minus 1, you can do. And then also, it's a nice quick induction. There's a wonderful counting argument. Anytime you have factorials, there's got to be a permutation there somewhere. So some great counting arguments there. One more type of conjecture I want to show you. And so again, how can you tell from this factorial representation, so again, the minimal one, whether an integer is even or odd? And if you see the answer to that, I would add to it whether or not it's divisible by 3, and again, to state your answer as a conjecture. And I want to give you a visual to help you see that. So think of n, I don't know how high up it goes, but something times 4 factorial, something times 3, something times 2 factorial, sometimes 1. So I'd like you to think for a minute, how could you tell, if I filled in the blanks for you, how would you know immediately whether it's even and odd? And if you get that one, how would you know immediately whether it's divisible by 3? So let's think and pair on this again, will you? How would you know if it's even or odd? How would you know? Just so I can see your progress, how many of you think you know the answer to even odd? Keep going, keep going. Dan? I apologize again for not giving you enough time to figure this out. If students would get more time, sorry about that. We're going to get some reporting out on this. So can you find someone who can tell us the even odd one? So when is it even, when is it odd?
You have to look at the coefficient of 1 factorial. So if it's 0, if it's even, and then if it's 1, it's odd, because everything else is even.
I can't go that far. So you're looking at the coefficient of 1?
1 factorial.
Of 1 factorial. Yep, you are. Can someone tell me why that works? Pick on someone else. Can someone else tell me why that works? Why is only the 1 factorial matter for even and odd?
Because for 2, 3, 4, ... 2 is always going to be a factor of that n factorial.
Yep, so did you hear what he said? 2 divides all the other factorials. So 4 factorial is 4 times 3 times 2 times 1. There's a 2 in there, and there always is. Does that give you a little extra hint also as to the 3? Do you see now that you don't care what's in front of 3 factorial or 4 factorial or 5 factorial for determining divisibility by 3, because those all have a factor of 3 in it? Was that enough of a clue? Did I buy you enough time? Okay, someone tell me, how do you know it's divisible by 3?
It's divisible by 3 if and only if the coefficient of 1 factorial is equal to the coefficient of 2 factorial.
Oh, that is a really fabulously abstract way to answer that. So can someone give us, and it's correct, can someone give us, but I'm not sure everybody heard exactly, so let someone else give us the specific, so not him, somebody else gets the mic, sorry. Good answer though, really good answer. Someone else.
His conjecture was that it's divisible by 3 if and only if the first 2 coefficients are the same.
Someone make that specific for the rest of the crowd, okay? Just make sure everybody knows what we're doing here.
So every factorial number, 3 factorial and higher, is a multiple of 3. And so any linear combination of those is also a multiple of 3. So we only have to care about those first 2 digits. And so the only combination of those that makes a multiple of 3 is if they're both 0.
Yes?
Or if they're both 1.
Yes, thank you. And my students often just write down all the different things there for the last 2 once they figure the 3 factorial thing. So here's the conjecture. Very often my class only notices the 0, 0. And so we have a great opportunity to ask, well, is the converse true? Is that if and only if? Of course not. So I'm going to end there, not having told you a whole bunch of stuff you might want to know, and to ask the organizers if we do have time for a few questions. So thank you for participating. So these are just possible questions. I use this in class so that students can, sometimes, so students can say, I want to ask you number 7. And anyway, whatever, it doesn't matter. I'll have to read a few.
I don't actually have a question, Sue, but I want to thank you for modeling the IBL process for us. We spend a way too much time at this conference telling each other why we shouldn't talk to our students, and I loved doing the math. Thank you.
You're welcome. Thank you, Carol.
Number 4, please.
Number 4. This comes from, it works great. Yes, and these are the ones I know the answers to. So you can ask me other stuff, but you never know. Number 4, what course does this come from? This comes from a sophomore level discrete mathematics course that is required of all our math majors because I was chair and decided that was a good idea. And it's also taken by most of our computer science majors and all of our middle school licensure teachers. This comes in a unit in the course when we're talking about binary and hexadecimal because the comp sci people want us to cover that, if you will. And we're trying to help our future teachers really understand the base 10 number system. And frankly, they've seen base B enough times before we got to go someplace new for them to really experience thinking and learning about it. So that's both the course and the actual unit of context.
Well, I have one. Do you see any evidence that they actually take this skill and use it outside of the conjecturing exercises?
Yes. First of all, even when I try to lecture, they're always making conjectures, and everything I ask them, they're using that skill because we do it every day, often. The best evidence I have is that other professors sometimes complain when they get my students because in the middle of lectures, they're like, wait, let me figure it out. Where does this go? How does that work? I think it's like this. Is that right? And sometimes in a 30-student class, that can be hard to manage. So yeah, they do. They like conjecturing. It's a much shorter writing assignment to write a sentence than to write a proof, for example. So they like it and they take it with, is what we see.
This is a question for the room. In order to help clarify my understanding of what this community means by IBL. So if what just happened in this room fits inside of your idea of what IBL is, could you raise your hand? Cool. And if it falls outside of your idea of what IBL is, could you raise your hand?
No one's going to do that in front of me, but that's okay.
That's a way of forcing consensus.
That's right. You just force. I would tell you that I walked you through it here. That is not exactly how I would do it in the classroom. But this is a half an hour, 40 minutes in the classroom, not 12, which is my goal here. So.
We have time for one more.
Number 6. Oh, how does it relate to course content? It relates in like 10 different ways, which is what I like best about activities, is that they can cover, address, connect different concepts. So it's during a unit where we're talking about number representation systems. Earlier in the course, we've talked about divisibility. Later in the course, we're doing proof by induction and combinatorial proof. Anyway, it connects in multiple places. So I can do it kind of wherever in the middle of there I want. Anyway, they've done divisibility tests at base 10 in the homeworks. I mean, it sort of connects very organically to a number of different topics in the course. I try to have all the activities do that. We do about one a day. That took about 10 years to develop. Number 8. Yes, students make conjectures on in-class exams. My general rule for teaching a skill is to do it all the time, to tell them that's what you're doing, and to count it as part of the grade. And my students pay attention to what's going to be on the exam. So they do make conjectures on the exam. Pretty easy things usually. A lot of their work is not exam work. So.
Well, we are out of time, but please join me in thanking Sue Doree.
Thank you. My pleasure.